Yeah, so both of these are anti, right? The two BRs end up anti. You can see it, if it's on a ring, anti-addition on a ring will give you the trans diastereomers. Again, it's going to be racemic, so we'll have the enantiomer of this as well if it's chiral. In the halohydrin reaction, again, if it's on a ring, you get the ORs trans to the iodine. This is also racemic. Good questions. All right, I'm going to tell you what, I'll leave the halohydrin up for a second. I'll just alternate sections of board here. So the next reaction is anti-dihydroxylation. It's going to bear a lot of similarity. I'll let you get, I'll tell you what, I'll let you get this written down and then I'll let you get that written down at the top and then I'll explain the mechanism. So the reaction is the anti-addition of two OHs to that carbon-carbon double bond. MCPBA, that's a fun looking. In purple there above MCPBA is what the structure is. So it's metachloroperoxybenzoic acid. So if you don't have a chlorine there and you just have an OH there, that's benzoic acid. A carboxylic acid on a phenyl ring is benzoic acid. The OO bond, that makes it a peroxy, so it's a peroxybenzoic acid. And then the chlorine in the, so 1,3 position, 1,3 substitution of a benzene ring is meta substitution. Again, you're not going to have to know that until next semester. All right, so if you do this reaction, if you take an alkene, I keep using methyl cyclohexene. I hate using the same molecule every time. It seems boring. But it really illustrates well, like you get a tertiary carbon, you get a secondary carbon, the methyl gives you some stereochemistry. Right, you can do this reaction with basically any of these alkenes. All right, everybody got the product written down? I'm going to erase I'll get back to the product. Again, I may draw the enantiomer in the end. Okay, this is a racemic product again. I want to emphasize over and over, achiral starting materials and reagents. If everything that reacts is achiral, the product has to be racemic. Right? The only way to get a non-racemic chiral product is if something in the mixture is both chiral and optically active. Could be a catalyst, could be a reagent, could be the substrate itself. Something has to start out chiral. If you just have an achiral thing react with an achiral thing and then react with other achiral things, your product has to be racemic. All right. So, I like how everybody seems to call me between noon and 1. I was checking the time because our clock's down, but I have a whole, hope everything's all right. All right, so same thing is going to be true here in this reaction. This is basically The mechanism is obviously not that simple, right? Because the arrows I've just drawn would not give you what I'm going to draw. But the pi electrons react with the terminal oxygen. And then we break the OO bond. This reaction is really driven by the fact that the OO bond is really weak. I talked about that a little bit in the hydroboration reaction on Friday. The OO bond, oxygen and oxygen bond together really weakly. All right, so we attack the terminal oxygen. This H is actually going to end up on the carboxylate oxygen. How that happens is a little bit of a question mark. All right, so just draw it like this, and you can draw this product. I'm probably not going to ask you a mechanism to get to this. All right, and this is actually a reaction in itself. So if we don't have step 2 here, you can isolate the epoxide. The epoxides are really reactive. It's a 3-membered ring with an oxygen in it. So normally, right, that oxygen isn't going to be a leaving group. But because of the ring, because of that really highly strained 3-membered ring, if you can open up the 3-membered ring, you make the molecule a lot more stable. So if you just treat an alkene with MCPBA or any per acid, it's really this per acid bit that's the important thing. It will give you an epoxide. Right? So you could just stop there. This is the product of step 1. You know, I shouldn't draw an intermediate around that, should I? This is what you get.
Is it always the case for this type of reaction that the first step does not form an intermediate?
Yeah, the oxygen just goes on there. So this is also going to be a racemic. Again, the oxygen can come from the front, it can come from the back. The oxygen has to be on one side or the other of the molecule, right? The oxygen can't be in front of one carbon and behind the other carbon. Okay, so now step 2, H3O plus and water. Under acidic conditions, so you might notice here I've got 4 hydroxide. We actually have 2 different mechanisms here. So the first step is protonation of the epoxide oxygen. And again, I'm just drawing one stereoisomer. All right, so you protonate the epoxide, and now water can attack. And this, it looks just like the one above it. Right, so this iodonium ion, you have a 3-membered ring with a formally positive atom in it. So the nucleophile will do a backside attack on the more substituted position. That gets us the anti-stereochemistry. Still an intermediate, and then water will take that last acidic proton and this gets us our final product. I'll get out of the way in just a second, sorry. So 2 alcohols, they've added anti to racemic diol. Anti-addition, racemic, again, there's nothing chiral in there until the product. So alkene and a peracid gives us an epoxide. You can isolate that epoxide. So now the 3-membered ring, all the 3-membered rings, the one with mercury, the ones with halides, that atom is positive. We have a positive atom in there. So you can't really isolate the iodonium ion or the mercurinium ion. But with oxygen you can. It's still, the epoxides are reactive. All right, now though, once you take your epoxide, you dump it into aqueous acid, protonate the O, right? Kick out water. Now water can attack, again, it's an SN2-like mechanism on the carbon that would be the best carbocation. So usually the more substituted. That gets the anti-relationship of the two O's. Then have water come in and take that last proton. Right? Under acidic conditions, H3O+, you can't have hydroxide. There's not going to be any strong base in strong acid. You might note that I said down at the bottom you can do this with, sorry. All right, so down here I said H3O+ or hydroxide. I'll show the hydroxide mechanism up above. But the same thing here, if you use an alcohol, that OR winds up going on the more substituted carbon. So I'm going to take it from the epoxide here. And again, well, so that epoxide is chiral. And I'm probably not going to go into it. We're going to be strapped for time. Maybe after Thanksgiving I'll do it online. Figuring out how to make molecules like this optically active. So pharmaceuticals, if you're a chiral object, okay? Your biochemistry is chiral. So if you take a drug that's chiral, your body will react to the two enantiomers differently. And there's one famous case, thalidomide, where one enantiomer is a super anti-nausea agent, and one enantiomer is a mutagen. All right, so if you take the racemic, if say you're a pregnant woman taking the racemic drug because you're nauseous, the enantiomer that's an anti-nausea agent will calm you down, works great. But then your fetus is going to be mutated. That happened in the 50s and 60s before people really understood it. Why are you all looking at each other?
What do you mean they were mutated?
I mean, they were mutated. Most of them died. No, it was a terrible. You should look it up. Thalidomide. I really should talk about this more. A lot of I mean, it was marketed to pregnant women, right? So, like, who's going to want a nausea drug? Pregnant women. And this is one of those examples. There's a lot of both science policy, science error, public policy errors, right? So, like, who do we do all these tests on? Well, let's get a bunch of men and test it on them, right? So, I mean, this is sick, but I think it's a great anti-nausea drug. Why don't I get to take it? I ought to get to take that, all right? So they tested it on men. It worked great, seemed perfectly safe. It's the 1950s. It is actually really hard to make one enantiomer and not the other enantiomer. Even if you can make more of one than the other, you're going to get a significant amount of the other. So making enantiomers pure, that's what I was trying to get at. This is a huge problem. And a guy won a Nobel Prize because he figured out how to make epoxides and thus diols enantiomerically pure. So thalidomide, again, in the 50s, it was too expensive, they thought, to separate the two enantiomers, and it probably was, right? Like, we're going to be able to sell this drug for X amount of money. It's going to cost X plus $100 to purify one enantiomer, so just give them the racemic, right? It tests fine. And it took way too long to figure it out. So you ask what I mean. The most common thing to happen for pregnant women who took this drug was a miscarriage or a stillbirth. Like, that was way more common than anything else. And I would guess this generation, they were kind of maybe 20 years older than me. So there's probably some kids still around. My elementary school librarian only had one arm. Her right arm ended in a stub about here. And that was, I mean, she was lucky. That was the only effect she had. Right? So if you just go in and randomly mutate genes in a person, in a fetus, most likely thing to happen, probably the two most likely things to happen are death and nothing. There's a lot of the genome you can screw up and nothing happens. I mean, that actually is what happens. That's how evolution works, right? There are mutations. But for a lot, tens of thousands of babies were born with, in some cases, really extreme birth defects. So, I mean, this is why stereochemistry is really important. You're like, oh, wait, why didn't you tell me this back then? If you look that up and read about it, like I said, there's a lot of policy implications, there's a lot of chemistry implications. Point now is, if you want to market a drug and it's chiral, you have to make it in antimerically pure, or you have to prove that both, the safety of both enantiomers. It's hard to prove a negative. So, and you need to test it on a much wider population, right? If you just test a drug on a bunch of white guys, so any racial differences will be lost. Gender differences have been a problem forever. We always test things. We do medical tests, mostly on men. You've probably read about how, so heart attacks tend to manifest in women different than in men. But all the symptoms are, if you look at a textbook, like what does a heart attack look like, it's always for men. So women show up with all these symptoms, they get dismissed, they die a couple of days later. On the flip side, there was a point in the 70s when iron deficiency was identified as a problem, right? It was identified as a problem in men. They just told everybody, okay, women are having all these iron deficiency problems, everybody take iron. And so a bunch of guys started taking a bunch of iron. And men and women bleed differently, right? I don't want to get into too much detail, it's a chemistry class. Women had iron deficiency for a very obvious reason. Men took a bunch of iron pills, you can take too much iron and get in trouble. And so, point is, you need to test whatever, drugs, practices, symptoms, whatever it is, you need to look at entire populations. Okay, have I blown the whole class? Yeah, pretty much. All right, making an epoxide optically active is difficult. I'm going to say this is racemic, but if this was optically active, now your products would be optically active, okay? The backside attack, if this is a pure enantiomer, the next product is going to be pure. So here, if we use, and I think let me use sodium methoxide here, right? This could be hydroxide. This could be any strong nucleophile. All right? Really, any of the strong nucleophiles you guys have seen so far can do this reaction. That O- is going to attack, and here's the thing. Now it's going to attack the less substituted carbon. So this is purely an SN2 reaction. Stereochemistry on the more substituted carbon stays put. Oh, sorry, that's an O-. It's a backside attack, so we invert the carbon that gets attacked. So the strong nucleophile attacks the less, because it's being driven by the nucleophile, it attacks the less substituted carbon. And then this is probably going to be run, this would be run in methanol. And so now you finish the reaction by that O- grabbing a proton off the methanol. And again, this is either, if you do this with racemic product, you get, or if you do this with racemic starting material, you get racemic product. If you do it with optically active starting material, you get optically active product. So strong nucleophile, so under basic conditions, this reaction is driven by the nucleophile. The less substituted carbon is attacked. It's a backside attack, So if the O is back, if the epoxide O is back, the nucleophile is going to come from the front, vice versa. You release an O minus, and again, this O minus is usually, like in chapter 7, you would tell me that that's not a good leaving group, and it's not. What drives the reaction is the relief of this ring string. So this only happens in a 3-membered ring, right? All right. I'm going to throw up one last reaction at you. I might ask you that mechanism. I will not ask you this mechanism. And when I said the guy won a Nobel Prize for figuring out how to make optically active epoxide, he also figured out how to do this reaction optically active, figured out how to do a lot of reactions optically active. It was, still is. He's done enough, he might win another Nobel Prize. Anyway, if you take an alkene, and the reagent I want you to remember out of this, right, this is the last thing I'll put up. This is basically pure memorization for you guys at this point. Osmium tetroxide, OSO4. If you see that, the product's going to be a syn diol. Okay, so the 2 O's come from the same side, so you get 1, 2 diols with the 2 O's cis to each other if it's a ring. You can't really do this with an alcohol to get the OH and the OR. It's just going to always be 2 OHs. You do not have to know a mechanism on this. This is basically, can you memorize a reaction? Again, the book goes into a lot more detail on this one. I figure I'm just asking you to know it, and so I don't have to talk about it for 20 minutes and tell you cool stories about it. So I'd like to. It is exactly time, and I have 4 new calls. Something terrible has happened in the world. Any questions about what we've done today? All right, so like I said, if you guys, I think most of you are Monday students. If you want to come on Wednesday, like I said, if we fill up, I'll have to turn people away. But if you want to come, if you enjoy being in class, feel free. And you'll get your exam tomorrow in lab. What are you guys doing in lab tomorrow?